So here I'm going to talk to you about nucleophile trends. In other words, what makes a nucleophile a good nucleophile. So keep in mind, underpinning all of this is the fact that a nucleophile is simply a pair of electrons. And if I were to ask you to define what a base is, you would also say it's a pair of electrons. And what's the difference between a nucleophile and a base? Well, a base is always a nucleophile that happens to be attacking a proton. A nucleophile is always a Lewis base. And so the question really comes down to what's the distinction between nucleophile and base? Well, there's not a lot, because a nucleophile is always a Lewis base, but a base in the Bronsted-Lowry sense is simply a nucleophile that tends to want to prefer to attack a proton. A lot of overlap between nucleophile and base. They are significantly overlapping terms, almost completely overlapping terms, but not quite. And so what that means is that though these trends largely parallel those that we had for the acid-base reactions, the pKa's, not entirely, not when it comes to the way that these react with non-hydrogen substrates, non-proton substrates. So anyway, what we're going to do here in this video is cover nucleophile trends, which again, highly related to but not exactly the same as basicity, and what they basically amount to are these four things. Size of the atom that is the nucleophile, the bigger it is, the better. But if you have extraneous stuff, sterics, behind that attacking atom, then that's actually bad. The more minus you have, the better. So if something is more minus, it definitely wants to react more. But ironically, the electronegativity of the atom that's doing the attacking, the more electronegative it is, that's kind of bad for a nucleophile, because what it means essentially is that it doesn't necessarily want to react. And the whole point of a nucleophile is it needs to react with a nucleus in order to make that minus go away. So the more electronegative the atom is, the more likely it is to be happy just hanging out holding its charge, and so potentially it needs to not react. So the most important trend to illustrate first is essentially that, the size of the attacking atom. The bigger that is, the better off it'll be. And so what you want to think about is that iodine is going to be a better nucleophile than bromine, which is going to be a better nucleophile than chlorine, which is going to be a much, much better nucleophile than fluorine, and that's largely because of the size involved. Iodide is huge, bromine much less so, chlorine less than that, and fluorine is essentially very, very small, a tiny, almost point charge. And the explanation that's usually given for that is one that's called polarizability. But what you need to have in mind while you're thinking about it is this particular image, which is to say you have the carbon being, with a leaving group bound onto it, being attacked by the nucleophile, which is coming in from this side. So the carbon with the leaving group is here, and what I've illustrated in orange is the sigma star orbital that's actually getting attacked. So the lowest unoccupied molecular orbital, which is the sigma star of the carbon leaving group bond. And so you've got this relatively large lobe here, and then this tiny lobe and a small one, a node running right there, and so on. And your nucleophile's coming in from the back, and the closer it needs to get before it starts interacting with that orbital, obviously the less nucleophilic it is. And so the size argument essentially is fluorine's tiny, so it really needs to get up in there tight close to the carbon in order to have any effect and kick out the leaving group, whereas an iodide's much larger and it can start interacting with it from further away. But that doesn't quite capture the polarizability argument either, and what that basically says is you've got a minus charge over here, and you've got a substantial amount of delta plus on this carbon, and so that delta plus right there is going to start distorting the cloud of electrons that's around. So not only is this iodide bigger in space, but it has a electron cloud that's more easily distorted, and so the presence of a nearby plus will tend to distort this and make this sort of not spherical anymore, but instead moving in this direction more as you get closer to the plus. And that's a bigger effect on an iodine than it is on a chlorine. Said another way, because the iodide is so big, the electron cloud is held relatively loosely, and it's a lot easier to deform it in the direction of any plus, and then it will start interacting with this orbital even further out than you might expect. Bigger attacking atom is definitely better. So iodide better than chlorine, and so on and so forth. But this trend will hold for any number of other situations. So even for the non-halogens, if you just simply go down the periodic table one more atom than you started, the next one down is always going to be bigger, more polarizable, a better nucleophile. So in other words, a phosphorus is always a better nucleophile than a nitrogen, a sulfur is always a better nucleophile than an oxygen, and so on and so forth. So the key trend, and the one to remember if you don't remember anything else, is the size of the atom doing the attacking matters a lot, and the bigger it is, the more nucleophilic your nucleophile can be. However, that's for the size of the thing doing the attacking, so if you're comparing iodide versus, say, chlorine. But especially as we move on to more interesting synthetic operations, you're not interested in just simply using a halogen to do this displacement. Instead, you might have an oxygen doing a displacement that has some other group on it as a way of bringing together different molecules. For instance, what I have here is this oxygen that has a tert-butyl group sitting behind it. So that's, 4 carbons and 9 hydrogens bound to this oxygen. And that's a fairly large and substantially bulky group. And so that's what we are talking about when we say sterics. Stuff that's behind the atom of interest. So what what I have in this series is an illustration of an O- doing the attacking in all cases. But the bigger the group, the more bulk that's behind the oxygen, the slower any nucleophilic attack will be. Obviously, this oxygen is the same size in all three of these groups, all three of these nucleophilic partners, but this has a lot more stuff behind it and much greater chance that this will run into things and keep the oxygen from getting where it needs to go. So a tert butoxide is going to be much worse of a nucleophile than a methyl, which is substantially smaller. And then, of course, methyl is going to be worse than hydroxide, which is even smaller. So tert butoxide is a worse nucleophile than methoxide, which is substantially worse than hydroxide. And again, what we're illustrating here is the sterics, the stuff that's behind the interesting group. The less stuff you have back there, the better, the more nucleophilic your nucleophile will be. And this is really illustrated here in the methylamine. Once deprotonated, it'll be methylamide. This is a very good nucleophile. It's also strongly basic, very strongly basic, but it's a good nucleophile. Here, lithium diisopropyl amide is essentially not nucleophilic at all. There's so much stuff surrounding this nitrogen that it's just too large to be a decent nucleophile. On the other hand, it's an outstanding base, and the pKa for this is on the order of 42 or thereabouts. Keep in mind, the pKa for this is also pretty high. We would sort of generically think it's about 35. But in any event, this is so large and so bulky that it essentially can only serve as a nucleophile if it's attacking a proton, which is tiny. So this is functionally just a base and not a nucleophile, whereas the methylamide is both a nucleophile and a base, kind of depending. It's small enough that it can serve as a nucleophile, but obviously it's still fairly basic. The more stuff you have behind the group, the slower your nucleophile will be to react. Said another way, the less stuff you have back there, the more nucleophilic your nucleophile will be. I hope this goes without saying because we're talking about a nucleophile, but a nucleophile fundamentally is a pair of electrons that's going to do an attack, and the more charge involved, the more likely that is to do an attack. So the more minus charge present on your nucleophile, the more likely it is to attack. The more that your nucleophile is neutral, the less likely it is to attack. So methoxide is going to be a vastly better nucleophile than methanol, which is not particularly nucleophilic. This doesn't really want to react with something else and pick up a plus charge. This has a minus charge that it's itching to get rid of and would absolutely react if you gave it a chance. So along those lines, methylamide is going to be a vastly better nucleophile than methylamine. And of course, what I'm illustrating here is that ammonium is simply not a nucleophile at all. And if you think that this is a nucleophile, then you have a substantial problem and you need to address it. This does not contain a lone pair. This is just a plus charge. There is no electron density here to exploit. This cannot be interested in creating a new bond with something that is positively charged itself. In fact, it's going to be repelled by it. However, what's odd about this is the more electron density you have is good, but the more electronegativity of the atom doing the attacking, that's actually bad. And so this is illustrated by this trend here, where a methyl group with a minus on it is desperate to get rid of that charge. It's one of the strongest bases, but it will react in the nucleophilic sense if it has the chance. It will simply react with anything that will take away its minus charge. A nitrogen is not quite as indiscriminate. It will react with most things and very quickly, but the methyl will abstract a proton from anywhere and will likewise serve as a strong nucleophile no matter what. A nitrogen is not quite that desperate to make a bond. A hydroxide is many orders of magnitude less likely to make a bond. It's nowhere near as basic by about 20 units than the amide. So again, same idea. This is not nearly as nucleophilic. And then fluorine is tiny and perfectly happy have that minus charge to some extent. So it's not particularly nucleophilic at all. The less electronegative that atom is, the more likely it is to react immediately if you force it to have a minus charge. But this does, by the way, extend to a relatively simple series here where you have nitrogen versus oxygen in the case of just trying to do a simple nucleophilic attack on something. And so now I'm going to illustrate what happens when you have successfully run this attack. In the case of the nitrogen attacking some R group and ending up positively charged, you get that structure. And then of course, if the oxygen serves as a nucleophile and ends up positively charged, you get this structure. And so now the question is, which of those structures do you prefer? And the answer is clearly, you'd rather have the nitrogen plus than the oxygen. And I want to use the reaction coordinate diagram to illustrate this point a little bit here, that initially if you're looking at, say, this amine and this alcohol, they're not going to be that different from each other in energy. So we can just assume, for the sake of argument, that they're going to show up as having very similar energies to each other. However, once you get out to the intermediate, once you get out to the place where the nitrogen is briefly positively charged and the oxygen is briefly positively charged, then you know, since the nitrogen can better tolerate having a positive charge on it that you're going to end up with a lower energy for that new system than you did for the original. You're going to end up with a lower energy for the nitrogen containing with the nucleophile now installed than you would for the oxygen with the nucleophile installed. So again, what I'm illustrating is that the starting materials are roughly in the same place. There's not much difference in them, but it's clearly better to have a plus charge on a nitrogen than it is on an oxygen, which means that the intermediates that you form once the nucleophile has attacked, but before any acid-base reactions, the nitrogen is going to be substantially lower in energy than the oxygen is. However, what you may not have thought of is that that implies a higher activation energy to get there as well. It's harder to get to that higher point. So not only do you end up in a higher place in terms of the intermediates, but you actually have to go over a higher hump to get there. And so what I just simply illustrate is that trend. So even though it's not really about where you're going to end up, the fact that this energy is so much lower means that nitrogen is a better nucleophile. It's easier to go ahead and do that attack. It's harder to do the attack with the oxygen, with the alcohol. So the core idea, of course, is that the nitrogen ends up making a better intermediate than the oxygen does, but that inherently implies that nitrogen is a better nucleophile than the oxygen is, because it's an easier path to arrive at this lower energy substrate than it is to go to the higher energy substrate. The core idea, again, for the nucleophile trends is size of the atom doing the attacking. The bigger it is, the better, but extra size behind that is bad. Sterics are bad. The more minus it is, the better off you are, but the more electronegativity you have, the less nucleophilic it will be. Said another way, nitrogen is a better nucleophile than oxygen is, at least in part because it's not as electronegative, which means it's going to tolerate the plus better.